Hello and welcome to this fifth lesson in this course on metric and topological spaces. In this lesson we're going to be looking at functions between metric spaces. And as always, in the description is the booklet for you to follow along and work through the examples on and the solutions. So we're going to start by looking at continuity. And before we look at a mathematical definition of continuity, we're going to look at a couple of motivating examples. So on the left here we have a function that's continuous, and on the right it's not. It's got a jump in it. So if we look at the function at the right and we look at this point here, just a random point for now, then no matter how far or how close we want to have a look along the y-axis, so we can call that small distance delta, no matter how small delta is, we can find another point that's a distance epsilon away such that the distance in y is smaller than delta. So in other words, and then if we wanted to make delta smaller, we could shrink epsilon accordingly such that the y coordinates of those 2 points always stays less than delta, or rather the difference between them stays less than delta. However, for a non-continuous function, as this one here has a jump, if we try and make delta smaller than the distance in that jump, well, we can no longer find an epsilon such that the two points that are separated in x, a distance epsilon apart, have y coordinates that are less than delta apart. So no matter, even if we made epsilon 0, the 2 points would have to have a y coordinate that's at least delta apart, even if we made epsilon 0. Then if we made delta any smaller than that, it just wouldn't work at all. Let's now look at a formal definition of continuity. So if AD and BD prime are metric spaces, and f maps a to d, and this is a function, then we say the function f is continuous at a point a in the domain, and will often drop, but it's always implied that it's with respect to the metrics d and d prime, if for any delta greater than 0 there exists an epsilon greater than 0 such that d prime of f of x, f of a is less than delta whenever d of x and a is less than epsilon. So what that means is, however close we want to be in our codomain b, so that is the distance between f of x and f of a, we want that to be less than delta, then we can always find an epsilon such that if the 2 points in the domain, x and a, are less than a distance epsilon apart, then the image of those 2 points is necessarily closer together than delta. And note that some books will use epsilon and delta the other way around. But just be careful when you're reading other definitions, which way round they get epsilon and delta. And then finally, in order to say that the function f is continuous, then that's the same as saying it is continuous everywhere, so at every point A. So the first definition just tells us about the single point A, but to say f is continuous, that must be true everywhere. And then also, the notion of continuity depends on the choice of metric. So for one metric, a function might be continuous. You change that metric on either the domain or the codomain, and then suddenly it's not anymore. Right, for our first example, we want to show that the function f, which is given by f of x equals 2x, is continuous. And d here is the Euclidean metric, which in 1D just reduces to the modulus of the difference. And note that we use this bracket notation as a shorthand to also specify the metrics. Remember, functions, we normally just say set and then what set it maps to. We're going to include the metrics just because they're going to keep changing. And this is a bit easier to write. So in order to show it's continuous, we're going to start by showing it's continuous at a point A in R. Then we're going to give any delta greater than 0, and we want to find an epsilon that makes f of x minus f of a less than delta. For now, we're just going to set epsilon equals delta over 3. This is not a unique epsilon. Anything smaller than this would have to work. And also, it may not always be obvious what epsilon should be. Sometimes you have to play around with the function and really get a handle on it before you can work out what epsilon is. However, for now, I've told you, it's delta over 3. So we're going to consider a point x such that x minus a is less than epsilon. So now to show it's continuous, we want to show that f of x minus f of a is less than delta. So f of x minus f of a is equal to 2x minus 2a, which is 2x minus a. Now this is less than 2 epsilon, which is equal to 2/3 of delta, which is less than delta. So what we have shown here, for a given delta, we can find an epsilon such that if x minus a is less than epsilon, then f of x minus f of a is less than delta. Therefore, f is continuous at a, but we wanted to show it's continuous everywhere. So because a is arbitrary, we can say that f is continuous everywhere. None of the steps we did required a to be a specific value or within a specific range. Okay, for the next example, we want to show that the same function is not continuous. But the difference here is that the image or the codomain has a different metric. It has the discrete metric. So that was the distance between the 2 points is 0 if they're the same point, or 1 if they're different. So we want to show this is not continuous. If you want to have a go by yourself, pause the video and then come back to the solution. If not, and I understand using these different metrics is quite abstract, I'll go through the solution and then we've got a couple more questions that are quite similar to go through. So you'll have more time to practice. Okay, I'm going to go through the solutions. So as always, we're going to consider an arbitrary point A. Now, given any delta less than 1, the only points that satisfy f of x minus f of a being less than delta are those where f of x equals f of a. So remember that the distance between the 2 points was either 0 or 1 if they were different. Therefore, x must equal a. If this were a different function that was multi-valued, we could say there could be multiple values for a, but in our case, it's monatomic, so x equals a is the only solution. But any choice of epsilon, as long as it's greater than 0, would include other points. So therefore, we cannot find an epsilon that satisfies our requirements. That is, if we find a second point x such that x minus a was less than epsilon, then we want f of x minus f of a to be less than delta. We can't find an epsilon greater than 0 that does that. The only one we can find is if epsilon equals 0. But that doesn't satisfy our definition. And therefore, f is not continuous. Okay, this example is quite similar. The difference is we've swapped whether it's the domain or the codomain that has the discrete metric or the Euclidean metric. So have a go at this on your own and then come back to the video. So now you've had a go, let's show that f is continuous when we have these metrics. So as always, we're going to consider an arbitrary point A. Then for any epsilon between 0 and 1, the set of points satisfying d of a and x is less than epsilon is just the single point A. Therefore, any epsilon between 0 and 1, we just get that single point. Therefore, all points satisfying d of ax is less than epsilon, then f of x minus f of a is equal to 0, which is always less than delta, no matter what we pick delta to be. Therefore, f is continuous at a. And if a is arbitrary, then it is continuous everywhere. Note that this is a general pattern. It's not 100% always true, but often if the codomain is the discrete metric, the function is not continuous, but if the domain is the discrete metric, then it will be continuous. That's not always true, but in general, I think it seems to be. For the next example, show that the same function f, but this time defined on the set of integers, is continuous. Which is odd, maybe. You can see the function there, and it definitely doesn't look continuous. It's a series of dots. Okay, have a go on your own and then come back to the video. Okay, now you've had a go. We're going to start off by considering the arbitrary point a and z. So a is just an arbitrary integer. And we're also going to just have an arbitrary delta greater than 0. Now for any epsilon less than 1, then the set of points satisfying that the distance between a and x is less than epsilon is just that single point a. So in the real line, this wasn't the case. That set contained a lot of points. But now, because there's nothing in between the integers, it just is that single point. Therefore, for all points satisfying the distance between a and x is less than epsilon, the difference between f of x and f of a is 0, which is always less than that is always less than delta. Therefore, the function is continuous at a. However, a is arbitrary, and hence f is continuous everywhere. And this is maybe a little warning that just because something might look continuous or not continuous, it may not be what you think. Drawing lines on the real numbers or on a 2D plane can help build intuition for metric spaces, but you still have to be rigorous. Sometimes that intuition can lead you astray. And I guess the lesson here is that continuity depends both on the set of the domain and the codomain and the metric on both of those. The same function can change between continuous and not whenever you change the sets or the metric. Let's now look at some properties of continuous functions. The two theorems I'm going to present both have their proofs in the booklet, so when I put them up, pause the video and read through the proofs. So the first theorem is that if f and g are both continuous functions, then the composition g after f is also continuous. Again, the proof for this is in the booklet. Okay, now you've read through that. Our next theorem is that if f is continuous and we have a sequence an in the domain A that converges to a point little a, then the sequence f of a sub n converges to f of a. So that is, if you take a sequence, you map all of the individual points to the codomain, then that converges to the map of the limit point. Maybe just what you'd expect, but if a function wasn't continuous, this theorem wouldn't hold. So have a read through the proof and then come back to the video. Okay, now you've been able to read through the theorems, let's go through an example. So if we have a sequence of real numbers, which is given by 1 over n, well, this clearly converges to 0. But then if we take the function, so the discontinuous function, f of x, which is 1 for any x that's less than or equal to 0, or it's 0 if x is greater than 0. So this is clearly not continuous, there's a step at 0. Show that the sequence given by f of xn does not converge to f of 0. Okay, have a go on your own, then I'll put the solutions up. Okay, now you've had a think about that. So we know that f of x sub n is equal to 0, because for all of the x sub n that are greater than 0, therefore f of x sub n is always 0. Therefore, this sequence converges to 0. However, f of 0 is 1. And therefore, these two things are not the same, so it doesn't converge to the right point. So we've just seen the notion of an isometry, and just because we can find an isometry or one isometry between two metric spaces, that doesn't mean that the two metric spaces are equivalent. So we need a slightly stronger definition for that. So if we have AD and BD prime be metric spaces and F be a bijective function. So remember, bijective means that we can invert F, and it means we can match up every single element in A with a single unique element in B. So as sets, A and B are equivalent. That is, they're isomorphic as sets. Now we wanted to obey the following two conditions. So firstly, we want D of xy to equal D prime of f of x, f of y for any 2 points in A. That is, F is an isometry, it's length preserving. Similarly, we want D prime of xy to equal D of f inverse of x, f inverse of y for any 2 points in B. So that is, the inverse is length preserving as well. And in this case, we would say that AD and BD prime are isometric, or they're metrically equivalent. That is, anything we kind of care about in terms of metric spaces on one must hold for the other. And note that because F is bijective, any one of the two conditions automatically implies the other one. So actually we only need to check it, say for the top condition, the second one happens for free. And then finally, in this case, we would say that F defines the metric space equivalence. So you might say, so if you were to hear the phrase A and B are isometric and F defines that equivalence, that just means that F and F inverse are isometries. Note that Mendelssohn calls the two functions here f and g instead of f and f inverse, but it is exactly the same thing. And then finally, if we know that f defines the metric space equivalent, that is f and f inverse are both isometries, then we automatically know that f is continuous. So let's look at a few more examples. So for our first example, we have the metric space r squared with the Euclidean metric, and we want to show that rotations by the angle theta, which is given by the function there, show that this is an isometry. And this is what you'd expect from an isometry. You know that in normal space, if you rotate things, the distances don't change. So how could we show that? So if we look at the distance between x prime and y prime, we get this complicated square root, which I'm not going to read out. But if we expand the brackets, we're going to get cos squareds plus sine squareds everywhere. And they're just 1. So we end up with x squared plus y squared, which is equal to dxy. So this is an isometry, because for any dxy, that's equal to d of x prime y prime. Okay, for our next example, consider the same metric space, but now show that enlargements by the scale factor s are not an isometry. And again, this is what you'd expect. If something expands, all the distances grow. So have a go on your own, and then come back to the video. Okay, now you've had a go. We'll go through the solutions. So firstly, d of x prime y prime equal to sx squared plus sy squared square rooted. We can pull out a factor of s. So this is equal to s dxy. Now this clearly isn't an isometry because the distance after is not the same as the distance before. For our first example, we want to show that the function f, given here, is an isometry when both n and r have that metric. And then also, does f generate a metric space equivalency? So the way to show that this is an isometry is that if you add 1 to both x and y, then the difference x minus y is unchanged. So the distances remain the same. However, it does not generate a metric space equivalency. The reason for that is that it's not surjective and therefore can't be inverted, and so we don't get the both conditions we need. And the way to see it's not surjective is to show that firstly, because we're only mapping from the naturals, the only points in the codomain that we can map back to n will be integers greater than 1. Okay, we have our next example. We want the metric space of sequences of real numbers, where dl squared was just like the Euclidean metric, where if you have two sequences, you take them away element-wise, square that, then add all those up, and then square root it. And this function f is defined here, where essentially we just take every element in the sequence and we shift it one position to the right. Is this an isometry, and does it define a metric space equivalency? So it is an isometry, and the way to see that if we shift everything over to the right, well, the differences of the individual elements will remain the same. And then when you add them all up, they'll all remain the same. And that first element, because both of the sequences we want to measure the distances between will both have that first element 0, that won't contribute to the sum. However, it does not define a metric space equivalency. And again, the reason is that it's not surjective and therefore it can't be inverted. That is, any sequence that has an element different from 0 in that first slot, you can't invert. Nothing will get mapped to that.